As I was looking at this, I realized that actually we're not going to want to plot this because this will tell us the trajectory. Kind of. These are the parameterized equation because they have t. What we want to plot here is the actual slope field, because this is what we do because we're getting ready for when we cannot actually solve a system of differential equations, even though this one could be solved explicitly. And that's why they're giving us this, because really we didn't need this, because you use this to find the lambda values, and they are actually the coefficients of the solution. So we really didn't need it for that. We didn't need it for finding the critical points because they're not asking us to find critical points. So really, what we needed this for is to realize that it comes from this system, and here we're going to have an x and a y. And if I multiply x and a y by this, on the top I'm going to get this, and on the bottom I'm going to get this. And to display this in CalcPlot, all you have to do is click on this, which says Show System of DE's Notation. Then you click on this and it'll show you what the plot looks like. And as you can see, as we discussed, wherever we start, we're going to end up at 0. And if you click, it'll show you the trajectory that you'll take to get to that stable point. And as you see, we're approaching, if we're here, it looks like we're going straight to 0. But there's only one, we're only approaching this if we're on this line. And so this could be an eigenvector, and it is actually an eigenvector. And how do we say if it's this one or this one? Well, this one is the vector 1, 2. So let's try and plot the vector 1, 2. The vector 1, 2, and 0 for the z because it's in a plane. So this is the vector 1, 2. So we know that if we're on the vector 1, 2, we'll go straight to 0. And it's inverse. It's opposite. And why is that the case? Well, let's look at vector 1, 2. It looks like if we go to infinity, if t goes to infinity, this is going to become 0 faster than this because of this negative 6, because of the 6 in front. If I put e to the negative 6 times 1, that's going to be 1 over e to the 6, which is going to be way smaller than e to the negative 1, which is just going to be 1 over e. So the effect of this is going to cancel out pretty soon anywhere else. So anywhere else, as you see, we start from a location and then we end up going along this line right here. And what is this line right here? I am betting that it's this vector, because this vector will take a little longer to get to 0. And so eventually the sum of the two will get us closer to that vector. And so let's see if my theory is correct. I'll put this in orange, and let me add another vector. So select, no, I didn't want to do another vector field. I wanted to do another vector. So select vector right here, and we're going to put the other vector. So that's 2, negative 1. So 2, not this one. This one needs to stay at 1, 2. This one. 2, negative 1, and 0 because we're in 2D. And you see that it falls on what we are approaching from any other point. That's interesting, right? So as you see, if I start from anywhere else, and I don't know why it's doing this. As you see, as we're starting from anywhere else, we're going to approach this vector. So the bottom line is that the vector that is decreasing the lowest will be the dominating vector as we animate our thing, because here we can put an animation. How do you do that? Select slider, and we want to slide the T. And so animate, I got no T here. How about so in substance, in essence, what I wanted to say was that we're going to approach always 0, as we said initially. And what is the solution at 1, 1? Well, we can get the point 1, 1 and plot it in. And that's going to be 0. Click on this to show it. What is the nature of the solution at 1, 1? Well, if we could get this to... Hold on, let me just restart this. We're going to select a vector field. We're going to click on this. Then we're going to write negative 2x, negative 2y, minus 2y. Here I'm going to write negative 2x, negative 5y. And then we're going to display it. We're going to restrict to 2D. Then we're going to say to use a fixed length. We don't want a constant color. And now you're going to see that if I put the point 1, 1, 0, 1, 1, 0, and I click on this, this is going to be my solution. So this is what this guy describes in the xy plane. If we were to split this into 2 equations and take out the t and just put everything as a relation between x and y. And I hope this was useful, a little long, but we kind of understood how to use calcplot a little bit for these problems. And I'll see you next time.